Hello everyone. Let us continue our section 14 on factor groups. In theorem 14.1, we have seen that if phi is a homomorphism on G with the kernel of phi is equal to H, then we can have a factor group G over H. Also, we saw that if H is a normal subgroup of G, then we can define a factor group G over H, which we saw in theorem 14.5. Now we are going to see that if we have a factor group G over H when H is a normal subgroup, there exists a homomorphism gamma on G with the kernel of gamma is equal to H. Now this is theorem 14.9. So let us see the statement of this theorem. So let H be a normal subgroup of G, and we can see that there is a homomorphism gamma from G to G over H given by gamma of x is equal to xh, and it is a homomorphism with the kernel H. First we prove that it is a homomorphism. So for that, let x and y are two elements in G. We need to prove that gamma of xy is equal to gamma of x into gamma of y. For that, we start with the gamma of xy, and we can see that by definition it is xyh, which is same as xh into yh, and by definition of gamma, again it is gamma of x into gamma of y. So thus we proved that gamma is a homomorphism. Next we find the kernel of the homomorphism gamma. So kernel of gamma is the collection of all elements in G which are mapped to the identity element in G over H. That is, the identity element in G over H is H. Therefore the collection of all elements with the xh is equal to H. Now xh is equal to H only when x is an element of capital H. So we have proved that the kernel of this homomorphism is H, and you can see the single line proof in your textbook. Next we see the fundamental homomorphism theorem, which says that if phi is a homomorphism from G to G dash with the kernel of this homomorphism phi as H, then you can make it an onto homomorphism if G dash is replaced with the phi of square bracket of G. Then we know that by theorem 14.1, this factor group G over H is isomorphic to phi of square bracket of G under an isomorphism mu, where mu is from G over H to phi of square bracket of G, and which takes the element GH in G over H to phi of G. Now by the previous theorem, we can see that there is a map from G to G over H, and it is a homomorphism gamma with the kernel of that homomorphism as H, and that takes the element small g in capital G to the element GH, which is taken to phi of G under the map mu. That is, the phi of G, you can obtain phi of G by applying gamma on G and then mu on gamma of G. That is, we can have phi is equal to mu gamma, and this is called the fundamental homomorphism theorem. Now using this theorem, it is possible to classify the group Z4 cross Z2 over 0 cross Z2 with the help of the fundamental theorem of finitely generated abelian groups. So here we note that Z4 cross Z2 is a direct product containing two factors, and we know that a projection map takes a direct product to one of its factor. Now here we need 0 cross Z2 as a kernel of that homomorphism. So here we take the projection map which takes the direct product to its first factor Z4. That can be obtained by defining pi1 to be pi1 of xy to be x. So you have pi1 is a homomorphism since it's a projection, and the kernel of this projection is 0 cross Z2. Now we apply the previous theorem, and we have Z4 cross Z2 over the kernel, that is 0 cross Z2, is isomorphic to the image of pi1, that is Z4. We now see another theorem which gives us three equivalent conditions for a subgroup H to be a normal subgroup of G. The first one is G inverse is an element of H for every G in capital G and H in capital H. Second one is G inverse is equal to capital H for every G in G. And the third one is GH is equal to HG for all G in capital G. So here we first prove that 3 implies 1. So let us assume that the condition 3 holds, that is GH is equal to HG for every G in G. Since we need the condition for every G in G and H in H in the first condition, let H be an element of capital H. Then you can have GH, which belongs to the first set, should be an element in the second set, that is H1G for some H1 in capital H. Now post multiplication with the G inverse on both the sides of this equation, we get G inverse is equal to H1, which means that it is an element in capital H. So thus we proved that G inverse is an element of capital H for every G in G and H in H. So 3 implies 1. Next we prove that 1 implies 2. For that we assume the condition in 1, and in condition 2 we need to prove that two sets are equal. Using standard technique, we first prove that G inverse is a subset of H and H is a subset of G inverse. So let us assume the first condition, that is G inverse is an element of H for every G in G and H in H. But the collection of all elements of that form gives us G capital H G inverse. Now it becomes a subset of capital H. So thus we proved the first part. Next we prove that H is a subset of G inverse. For that we start with an element small h in capital H, and we choose an element G inverse in capital G. So as per condition 1, we have G inverse into H into G inverse should be an element of capital H. Now you can modify it to G inverse into H into G to be an element in capital H, means it is some H1 where H1 is in capital H. Now in order to obtain H on the left hand side of this equation, let us pre-multiply both sides of the equation with the G and post-multiply both sides of the equation with the G inverse, so that you can have H is equal to G H1 G inverse, which is a member of G capital H G inverse. So we started with H belongs to capital H and reached at H belongs to G capital H G inverse, which means that capital H is a subset of G G inverse. So thus we proved that G inverse and capital H are two equal sets, and hence we have condition 1 implies condition 2. Next we prove that condition 2 implies condition 3, which again we prove using two subset inequalities. So we assume that G inverse is H for every G in G, which means that any element in the first set is equal to H1 for some element H1 in capital H, which you can modify to GH is equal to H1G, and you can see that this H1G is an element in the set capital HG. So which means that G capital H is a subset of capital HG. Now to prove the reverse part, we start with the condition 2 but with an element of the form G inverse in capital G. So thus we have G inverse HG is an element of capital H, which means that it is some H2. So modifying, you can have HG is equal to GH2, and which is an element of the form G capital H. Thus we have capital HG is a subset of G capital H. Now together with the GH subset of HG, we obtain GH is equal to HG, that is condition 2 implies condition 3. Hence the proof of the theorem. So when we conclude, we have the following statements, that is when n is a normal subgroup of a group G, we can have the factor group of G by n, which is denoted with the G over n. And the binary operation in G over n is defined by an into bn is equal to abn, and the identity element of this factor group G over n is En, or it is n. Now there is a homomorphism from G to G over n, which can be defined by gamma of G is equal to Gn, where G is an element in capital G, and kernel of this homomorphism is n. So we conclude here, and you are requested to submit the answers of the homework that is given along with this video, and thank you.